Hi, in this video, we want to take a look at idempotent matrices. All right, so a square matrix is idempotent if a squared is equal to a. All right, so if I square something and I get, the item I was squaring, it's going to be idempotent. All right, so here are two examples, probably the two most common. If I square the identity matrix, I get the identity matrix, and if I square the zero matrix, I get the zero matrix. All right, so there's at least two. All right, so now here's a theorem for us. The only non-singular idempotent matrix is the identity matrix. Okay, well, let's do a proof by contradiction. Let's assume not. Let's say that there is a singular matrix that is idempotent. Sorry, there's a non-singular matrix that is idempotent, but it's not the identity matrix. Okay, so then what we're going to do, so it's non-singular, therefore it's going to have an inverse. All right, so we know that since by assumption a squared is equal to a, it has an inverse, and it's not equal to I. All right, so let's go ahead and go a squared is equal to a. All right, well now let's multiply both sides by the inverse. All right, well when I do that on the right, I'm going to get the identity. On the left, I'm going to get just a. So a equals I. That contradicts what I set up. Therefore, the assumptions cannot be correct. The assumptions of the proof by contradiction are not correct. And so it works out that the only non-singular idempotent matrix is the identity matrix. All right, if A is singular, symmetric, and idempotent, then A is positive semi-definite. Okay, so singular means it does not have an inverse. Symmetric means that the transpose is equal to itself. And idempotent is what we just defined. All right, so here's our proof. Let's say that A is equal to a squared, because that's by the idempotent assumption. Well, a squared is just a times a. Okay. Well, let's change this up. Let's go with A, replace that with A transpose. Why can I do that? Because it's symmetric. Okay, all right. So now, at this point, I've got that A is equal to A transpose A. All right, now let's take any non-zero vector and let's multiply by its transpose on the left and multiply by that vector on the right. So if I go up here, I go A transpose, or sorry, Y transpose A Y, and I do Y transpose A transpose A Y, like I have here. If I take a moment and look, I realize that this part right here is A times Y, transpose on the whole thing. So here I have A times Y transpose A times Y. Well, if we remember correctly, that's the 2 norm squared. The 2 norm can't be negative. All right, it can be 0. So we can see that immediately that this product cannot be negative because it's equal to a normed squared. All right, so it has to be 0 or positive, which means that A has to be positive semi-definite. Okay. All right, now let's think about the eigenvalues of idempotent matrices. Okay, so if I take a squared equal to a, then I can subtract a from both sides. All right, well, there's a little bit of some stuff I'm using to make this a complete proof. This is close enough for us. If I see that a squared minus a is equal to 0, I know that this divides a characteristic polynomial. It divides the minimum polynomial. Therefore, I can go over to this. This is going to be a divisor of the minimum polynomial, which is, so then I factor it. So here I can see that all the eigenvalues, or so the eigenvalues are going to have to be equal to 0 or 1. Now, there's a little bit more with this because of the minimum polynomial aspect, which we haven't talked about in this class, but it's true if you go into a proof-based linear algebra course, that from here, we know that all of the eigenvalues have like multiplicity 1. So it's a diagonalizable matrix. That's kind of a big deal. And so all eigenvalues of idempotent matrices are 0 or 1, and idempotent matrices are diagonalizable. If A is an n by n idempotent matrix with rank R, then A has R eigenvalues of 1 and n minus R eigenvalues of 0. Okay, well, let's go ahead and say that V is an eigenvector of A. Then A times V is equal to lambda times V. That's definition of an eigenvector. All right, well, let's do this again, but this time I'm going to go A squared. I'm going to take A squared V. Well, that's going to be A times lambda V, which gives us lambda squared V. Okay, so I know that AV has to be equal to A squared V, right? Well, that tells me that lambda V is equal to lambda squared V. Well, if I go through, and that this zero vector should not be there, or not in this position. There should be an equal sign. All right, so I'm missing an equal sign. Okay, so now if I go ahead and I factor, I get to this point. So I have the zero vector is equal to lambda minus 1 times V. Okay, well, when I look at this, remember eigenvectors are never equal to 0. So the only way that this can be equal to 0 is either lambda is equal to 0 or lambda is equal to 1. Okay, well, now let's think about the number. So the number of non-zero eigenvalues equals the rank. If we remember this from a previous lecture, the number of non-zero eigenvalues equals the rank. Therefore, the number of eigenvalues equal to 1 has to equal the rank of A. Therefore, there has to be R eigenvalues equal to 1. And then the n minus R part follows immediately. All right, so if A is idempotent with rank R, then the trace is equal to the rank of A. And really, that just comes from the fact that the eigenvalues are either 0 or 1. So remember, if I have if the rank is less than n, I'm going to have zeros for my eigenvalues. So when I take the trace is equal to the sum of the eigenvalues. Well, I know that all of these are 0 or 1. Well, how many zeros do I have? Well, the number of 0 eigenvalues. How many ones do I have? The number of 1 eigenvalues. And here I'm multiplying by 0, so that doesn't do anything for me. Adding up 0 doesn't do much for me. Well, number of times I add up 1 to itself is just going to be an integer. And how many eigenvalues equal to 1 do I have? Well, the rank of A. Easy peasy, lemon squeezy. All right, if A is an n by n idempotent matrix, P is n by n non-singular, then we get a whole bunch of things that happen. I minus A is also idempotent. A times I minus A is equal to 0, and I minus A times A is equal to 0. And one that's with a little bit of oomph for, a little bit juicier, if I take any non-singular P inverse AP is also idempotent. So why do we care about this? Well, what I can do, if I have an idempotent matrix, I can conjugate it on each side and get another idempotent matrix to fit my needs easily. All right, so let's say that for this next theorem, let A be n by P. Let's say it's rank R. What's a pirate's favorite letter? R. Okay, side note there. Let's say that A generalized inverse, so A superscript negative sign is the generalized inverse of A. And we're going to say that A transpose A, parentheses, superscript negative sign is the generalized inverse of A transpose A. Then all three of these matrices are also idempotent. Generalized inverse times A times generalized inverse. And then we get something, now this looks interesting, this looks exciting. If I have in the middle, A transpose A, generalized inverse, and I put A transpose on each side, this whole thing is also idempotent. And we're going to use this one later in the semester. All right, now this next one, there's actually 3 proofs in here. there's 3 proofs for the price of 1. So you're definitely getting a bargain today. If A is an n by n symmetric matrix, A is equal to the sum of some symmetric matrices. So what this is saying is I have a bunch of symmetric matrices and I add them up. I get A, then any 2 of these conditions implies the other one. So A is idempotent. All of the addends are idempotent, and AI times AJ is equal to 0 when I does not equal J. So any 2 of these implies the third one. So if I have idempotent, A is idempotent, and each of the addends are idempotent, then AI times AJ is equal to the 0 matrix. Now, if A is idempotent and AI times AJ is equal to the 0 matrix, then for free, we know that each of these sub-matrices is also idempotent. Okay, now, next one. If I know that each of the sub-matrices, each of the addends are idempotent, and I know that the product between any 2 different ones gives me the 0 matrix, then I know for free that A itself is idempotent. There's a lot going on in that theorem. Now, if I is equal to the sum of some symmetric matrices, and I have the rank of each of the addends is R sub I, and N is equal to the sum of the ranks, then first and foremost, each A sub I is idempotent for all I, and the product of any 2 distinct ones is going to be equal to the 0 matrix. All right, now we want to talk about vector and matrix calculus. All right, the main thing we're going to be focusing on here is we're going to be focused on derivatives. We're not going to really do a whole lot with integration in this situation. All right, let's go ahead and say that U is a function, is the output of a function that maps vectors to the real numbers. All right, then the derivative of this real number function is just going to be the vector of derivatives with respect to each component. Now, as we talk through this calculus part, we're going to make the assumption that the derivatives exist as needed. All right, so if you've taken mathematical analysis, if you've taken advanced calculus, you know that there are certain assumptions we have to have. What we're going to do, just whenever I need anything from calculus, I'm going to make the assumption that, well, we're only going to talk about cases where it makes sense to be doing calculus. I'm not going to be doing something like stochastic differential equations or anything like that. We're just keeping it real simple. It's just calculus. All right, so now there are bugs that are getting into my face. I don't know if the camera is picking them up, but they are bugging me. All right, so let's go ahead and say that U is equal to the transpose between a constant matrix, constant vector, and our random variable vector. Then the derivative of U with respect to our variable vector is just going to be the other vector in the dot product. So if I have A transpose X is my function, so X is the one with variables, A is constant, then the derivative of U with respect to the variable vector is just going to be the constant vector. And intuitively, this should be pretty obvious. I mean, this makes sense if you think about polynomial derivatives. All right, so the proof is just basically write it out. U is equal to the sum of AI xi. If I take the derivative with respect to xi, I get xi's coefficient, and therefore it just follows if I just write it out, and I got it. All right, now let's take this a little bit further. All right, so here the function was a product between 2 vectors. Now we want to take a look at if I take random variable vector transpose times a constant matrix times the random variable vector. And we're going to say that A is symmetric and constant. Then the derivative of U with respect to the random variable vector is, of course, it's going to be the partial derivative of what we defined U to be. And it's just going to be 2 times the constant matrix times our random variable vector. All right, so now for this next part, we want to kick this up a notch. We've been talking about vectors that have random variables in them. Now, what we're interested is in the situation where we have a matrix and we have variable entries. Okay, so let's go ahead and say that f of x, so this is matrix x, f of x is equal to u, and u is a real number. We're keeping it real, yo. The partial derivative of u with respect to x, oh, that should be matrix x. I wish I had a whiteboard so badly. It's just going to be the matrix of derivatives by entry position. And that's just the definition. All right, so now let's start using this a little bit. If u is equal to the trace of x times a, so x is our variable matrix, a is a constant matrix, x is p by p symmetric, a is p by p constant, then the derivative of u with respect to matrix x is equal to the partial derivative of the trace xa, and this is what's going to end up happening is that this is a plus a transpose minus the diagonal of a. Now, if you think about this, I'm going to have, so this is a symmetric, so the x has to be symmetric for this to work out. All right, so if I take the trace, this is just writing out the definition of the trace. If I take the derivative with respect to a particular variable, so now remember, x is symmetric, right? In this assumption, this assumption of the theorem is that x is symmetric. So when I take the derivative on it, I have two entries I'm taking the derivative on. So if I take the derivative with respect to xij, well, that's my coefficient is aij, but also aji because xji is the same value. Now, if I'm dealing with the diagonal, now this is when I does not equal j. If I'm on the diagonal, then I doesn't equal j, or I equals j, it should be an equal sign, and I get aii. Okay, so now, if you think about it, I've got two entries here, and here I've got two entries. But on the diagonal, I've only got one. So it's like this correction term subtracts off the extra. All right, now for our next trick, let's say that u is equal to natural log of the determinant of x. Now we're going to make an assumption about this. So we're natural log of a determinant. Okay, well, what we're going to go ahead and do, so if I think about what's the domain of natural log from college algebra? It's positive numbers, correct? Okay, so what we're going to do, we're going to go ahead and throw on an additional hypothesis that our variable matrix is p by p positive definite. Why do we really need this? Because otherwise the logarithm wouldn't make sense. Okay, so we're restricting our domain of matrices to things that make sense, that take a determinant and put it inside a logarithm. All right, so this function makes sense with this assumption. Now, if I take the derivative of natural log of the determinant of our variable matrix with respect to our variable matrix, this will be equal to 2 times the inverse matrix minus the diagonal of the inverse. Now, we're going to let A be non-singular of order n. And we're going to say that the derivative of A with respect to x exists, and the derivative of the inverse with respect to x inverse exists. Sorry. All right, so now, all we're doing here is we're just saying what I need exists to be able to pull this off. Then the derivative of the inverse is going to be equal to the negative inverse on each side of the derivative of A with respect to x. All right, so now I want to do an actual proof for you. It's not too bad. But this is a very standard trick in advanced calculus and mathematical analysis. This is like week 2 material. All right, so first and foremost, I'm going to go, I know that A inverse A is equal to the identity. Now, the identity is a constant value. So if I take its derivative, I have to get all zeros. That's going to come up later. All right, so now let's focus only on the left-hand side. Focus only on the left. If I want to take the derivative of this, then I've got like the product rule, right? If I multiply two things together and I take a derivative, I end up getting a product rule. Well, in matrices, we have a product rule, but it works out being a little bit uglier. It's not as pretty, but it's still beautiful. It's beautiful. All right, so here's what I'm going to do. I'm going to take a derivative just like I did before, back in the day during Calc 1. All right, so what I'm going to do, if you think about the proof of, or the derivation of the product rule, if you remember it, what you do, you take x plus delta x, you plug that in, you take x and you plug it in, you subtract, and then you divide by x plus delta x minus x. All right, that's what we're doing here. You notice I have x plus delta x, I put it into A inverse and A. Boom, I've got that. Now I'm going to put x into A inverse A. Remember, so we're treating A as the output of a variable. Now, remember, just like in regular calculus, I divide by the difference between x and x plus delta x. Okay, so you'll notice I haven't taken a limit yet. I'm just saying, so if you remember in Calc 1, before we took our limits, we had to get through all of our algebra. I'm doing my algebra step right here. All right, now, what I'm going to do, you see how I have a negative sign right there? Right in the middle, I'm going to add 0. Sounds exciting, right? To add 0. Adding 0 does nothing. Let's pause for a moment. I'm going to add something and I'm going to subtract it at the same time. If I add something and then I subtract the same thing, that's the same as adding 0, right? Doesn't change my equation. So what I'm going to do is I'm going to add A inverse of x, A plus x, A of x plus delta x. And I'm going to add and subtract the same thing. You notice I've got this here, and I subtract the same thing. So these two together cancel out. Or if they cancel out, it's okay for me to put it into the equation because it's the same thing. All right, so now what I'm going to do is I look at these two terms. I notice I have A of x plus delta x, A of x plus delta x. I'm going to factor out A of x plus delta x out. I look here, I see that I have A of x inverse, I have A of x inverse. What I'm going to do, I'm going to factor A of x inverse out. Okay, so when I do that, when I factor out A of x plus delta x, I get this term here. So these two, I factor A of x plus delta x, I get this part. Now over here, I'm going to factor out A of x inverse. When I do that, I get A of x inverse in front of this fraction. Now what I'm going to do is I'm going to take the limit as delta x goes to 0. Why do I do that? Well, when I do that, I know that this is going to become the derivative that I actually want. And when I do that, I'm going to look here, and I can see that this is going to be the derivative of A inverse with respect to x. When I take the limit as delta x goes to 0 here, I get A of x, which is just A. When I take the derivative on this, well, there's, that's just a constant for the purpose of the limit. And when I take the limit here, I know that's going to be the derivative of A with respect to x. So boom, I've got this. All right. Now, I know that if I come up here and I take the derivative of the left-hand side, I get this part. Now, what about I? If I take the derivative of I with respect to x, well, does I depend on x? No, it doesn't. It's a constant. What do we get when we take a derivative of a constant? We get 0. But we're dealing with matrices. Does it change? Well, I get the 0 matrix instead. All right. So I know here on the left-hand side, I get this item. On the right-hand side, when I take the derivative, I get 0. So I know that this has to be equal to the 0 matrix. Okay. Well, I'll go ahead and move part of it over. Oh, I dropped a negative sign. There should be a negative sign right here. In your notes, put a negative sign. All right, so now I see that I've got derivative of A inverse with respect to X times A is equal to negative A inverse derivative of A with respect to X. Well, can I get this derivative by itself? Yes, I just multiply both sides by the inverse and I have it on each side, and there should be a negative sign right there. And boom, we've got it. Okay, so now our next theorem. If A is n by n positive definite, then the natural log of the determinant of A is equal to the trace of A inverse derivative of A with respect to X. All right, so let's repeat that. If I take the derivative of the natural log of the determinant of A, that's equal to the trace of A inverse derivative of A with respect to X. All right, so how am I going to proceed? First and foremost, I'm going to prove this for diagonal matrices, and I'm going to use that in a moment to take it the rest of the way. So if I take the derivative of natural log of the determinant of a diagonal matrix, it's a diagonal matrix, the determinant is the product of the diagonals, and we know that that's going to be the product of the eigenvalues. Boom, we've got this. Now, I've got a logarithm of a product. This should absolutely like kick off bells and whistles in your mind. Natural log of a product is equivalent to the sum of natural logs. Boom, I've got this. All right, so what I've done so far was I replaced determinant of D with the eigenvalue formula. I recognize I'm taking a logarithm of a product, so I convert that to the sum of logarithms. Now, we have positive definite here because that guarantees that all the eigenvalues are positive, so then it makes sense to be doing this. All right, so now I can go through and I see that I have a derivative of a sum. Well, that's the same as the sum of derivatives. Okay, so now I just take the derivative of lambda with respect to X. Well, I know I'm going to use chain rule. Chain rule is going to be 1 over lambda, and then derivative of lambda with respect to X. Okay, now let's stop for a moment and let's think. Let's think about this. I have 1 over lambda. Well, 1 over lambda, doesn't that look a lot like the inverse of the diagonal matrix? Yes. Yes, it does. Now, what about here? The derivative of lambda with respect to X. Doesn't that look like the derivative of a diagonal matrix with respect to X? Yes. Yes, it does. So if I look at this for a moment, I can see that these are the diagonal entries of multiplying D inverse by the derivative of D. Well, if it's the diagonal entries and I'm adding up, then that has to be the trace. Boom, we got this, we got this. Okay, so now that proves this theorem, but only for diagonal matrices. We need to take this the rest of the way. All right, so what we're going to do, we're going to go ahead and say that A is equal to C times diagonal matrix times the transpose of the conjugating matrix, and C is orthonormal. All right, so that means that C transpose C is equal to the identity, and C times C transpose is equal to the identity. Okay, so if I think about A inverse derivative of A, all I'm doing is I take this CD, C transpose, and I insert that for A. Boom and boom. Okay, so now what I'm going to do, I'm going to use that product rule that we just showed how you derive a few moments ago. If I go through and I apply that whole product rule thing, I plug and chug it all the way through, I can see that a product rule is going to give me something like this. Now remember, order matters when I deal with matrix multiplication. So I have to preserve this order as is. Now, what I've got here, I've got C, D inverse C transpose. I can go through, I'm going to distribute to each of these. As I distribute, I can see that the C transpose C is going to cancel out. When I distribute here, C transpose C is going to cancel out. And this one's going to be a bit uglier. So now I have C, D inverse, derivative of D, C transpose, C, and the derivative of C transpose. And then I've got something a little bit juicier. Now, I'm going to take the trace. If I remember, the trace, I can change the order on the inside of the trace. When I do that, when I change the order, I've got C, C transpose, boom, those cancel. I've got, let's see, what else? I've got C, C transpose, boom, those cancel. All right, so I can see that I'm left with this. I've got this, and I've got that. Okay, so now, if I recognize that this is like the output of a product rule, well, I remember that the original product is going to give me the identity matrix. The derivative of the identity is 0. Therefore, I just get the rest of the way. And boom, we got it using the formula for determinants with eigenvalues. Well, that's all I got. Take care and goodbye.